So now let us look at this question. According to this question, example number 2.1 says that we have a one-dimensional steady state heat conduction. Okay, so heat conduction through a rectangular object like this. One dimensional. One dimensional means heat is transferred only in X direction and no heat generation. The moment they say no heat generation, one dimensional, all this information need to be very clear to you, because that's what you apply to solve the question. Okay, so then these are the boundary conditions. At X equals to 0, temperature X equals to 0 equals to T1. And then at X equals to F, temperature at F equals to T2. So now develop the expression for the temperature distribution Tx within the slab. So now the general equation, so all the time make sure you write the general equation related to rectangular coordinates. Okay, so you don't need to, of course, you don't need to memorize. To be given to you in the final exams or in the, you see it in the appendix of the exam paper. Okay, so it is, the solution is like this. We have 1 over alpha, sorry, 1 over alpha dt over the t. Again, this equals to d squared t over the x squared plus the squared t over the y squared plus the squared t over the z squared and plus q over k. So this is the equation related to the rectangular object. Heat transfer in three-dimensional coordinates, namely x, y, and z axis, and then with heat generation of all the parameters. So we are going to apply this boundary condition. So from the question itself, it says that one dimension. Okay, so it means that if it is one dimension, so it means y and z component will be taken out of the equation. So this is 1D, 1D. Okay, so steady state. Steady state means any parameter which depends on temperature, sorry, depends on time, will be equal to 0. You understand me? So it means which parameter depends on time? This t. You understand? So it means that this also goes to 0. This means steady state. Steady state condition. You understand? Then no heat generation. If there is no heat generation, it means what? No heat generation. Okay? So now you see that the question has been simplified to a very simple solution. So now you have the square t over the x squared equals to 0. We can also solve this question. Okay? So now we need to integrate this function. To find the temperature as a function of x, we need to integrate this. So if I integrate the second derivative of this function, integrate this is going to give me dt over the x, and this will give a constant c1. You integrate 0, you get a constant. Okay. Similarly, you have the t equals to c1 times dx. I integrate this also. Constant is there outside. So if I integrate temperature, again I'll get T. So Tx. And this gives me, if I integrate this, I'll get C1 X. Okay, so plus another constant C1. Okay, so sometimes you can also write T. It's also correct. But I want to show that T is a function of X.
Yeah.
So that's why I put my X over here. It's a function of X. So now we need to solve this C1 and C2. How do we determine C1 and C2? By applying boundary condition. You understand? So this is where this boundary condition is very important. If you don't know the boundary condition, then again, you cannot proceed in this way. You understand? So now, we will say at x equals to 0, t equals to what? T equals to, yes, so at x equals to 0, we will have t0. So t0 equals to t1. Okay, so then we will substitute into this. So I will have t1 equals to c1 times 0 plus c2. So it implies c2 equals to t1. And similarly, we can have, you want to find c2. Okay, so then at x equals to L, okay, at x equals to L implies TL equals to T2. So I have T2 equals to, substitute into this equation, okay, equals to C1 times what? L. Okay, plus C2. So C2 equals to this moves to the other side. Oh, so we know C1, sorry, plus C1, yes, that is. So this is T1. Okay, so now we will have C1 equals to T2 minus L. So now we know all our constants, C1 and C2. I'll substitute into this equation. So I'll have Tx equals to T2 minus T1 divided by L times X plus what? T1. So this is the solution to this. Temperature distribution Dx within the slab. So if you want to test whether your result is correct or not, all that you need to do is to substitute x if x equals to 0. What will be? T will be equal to T1. And if x equals to L, we have x equals to L here. This will be L, cancels out. T1 will cancel T1, there will be T2. It means this is the equation which governs the temperature distribution. So you can find the temperature at any point along the slab. So this is how interesting this particular topic is. You understand me? So it gives you a general idea about the temperature distribution across the surface of the rectangular surface or rectangular object. Okay. So now the next, it says determine the heat or develop the heat flow through the area of the slab. We want to find out how much heat is transferred, what is the heat flux through the slab. So all that we need to do, we know by definition, okay, by definition of heat flux equals to minus K A dt over dx. So all that I'm going to do, I have to differentiate this with respect to x. If I differentiate this function, so I have, let's say, dx equals to t2 minus t1 times x plus t1. So if I differentiate this, t over the x, that is being t2 minus t1 divided by plus 0. So temperature is constant. All these parameters are constant, only x and temperature are changing. So this is also constant. So this is where we have to apply your differentiation and integration. Very important. Please, you should revise this thing. So now, if I know the x equals to this, I only substitute it to this equation. And this is me. This equals to minus AA T minus T1 divided by L. So this is it. This is a heat flux. So if I know these parameters, I know the value for K, I know the value for A, I know T2, I know T1, I know L, I can easily calculate the value for Q. Okay. So the same thing is what we did. So the thermal resistance will come later on. It will be understood later on. It's premature to discuss that now. Okay? But when we say thermal resistance, it is, I'm not going to delay myself. So if we rearrange this equation, this becomes T1 minus T divided by L divided by K, that's A. And we define this new parameter, the combination of this to be what for thermal resistance.